Well, hello, ladies and gentlemen. Welcome back. We are continuing our discussion on vectors as we proceed into chapter 6 with 6.2, which is all about dot products of vectors. Dot product. So that is what this video is going to be focusing on, is the dot product of a vector. We're going to define what it is and how to calculate it. As you can see in further videos, we're going to be able to find the angle between two vectors and talk about things like orthogonal vectors and so on and so forth. But in this video, our goal is to define and calculate the dot product of a vector. So first and foremost, let's talk about the types of vector multiplication, okay? You are going to see in any kind of research about vector multiplication, all right, about the cross product and the dot product, okay? So now let's really focus here that we, in our course and curriculum, are only going to be talking about the dot product. The cross product is above our current pay grade, so we are not going to be diving into that. I did put in there what it results if you are interested for any further multiplication or for any further mathematics you're going to get into, but our dot product. Now, what are we going to see with a dot product? The most important thing to understand when it comes to the dot product is that when you take a dot product of two vectors, you get a scalar as a result. So you get a numeric number, a value, as a result of the dot product of two vectors, okay? Because two vectors multiplied together do not produce a vector, but they produce that real number, the scalar, okay? So what does a dot product actually look like? Well, let's go through some annotations first and foremost here. So let's say, for instance, okay, we are taking a look at a dot product. So what you are going to see is this notation for the dot, right? That is our dot product. What you don't want to do is you don't want to do that. That is going to be our cross product, which is not going to produce the same end result as our dot product does. So you do not want to do that x as a product. I know we think about it when we do multiplication, but we don't want to go ahead and do that. So the dot product, remember, turns out to be a scalar. That is why you see in the resultant the product of two real numbers, u1 and v1, and then the sum of two real numbers, u2 times v2. So that is going to produce a scalar or a real number value. So when you are multiplying these dot products, right, you are taking the x components, multiplying them, plus the y components and multiplying them. All right, so let's take a look here real quick at a couple other properties about dot products, just to kind of maybe save us a little bit of time as we continue on through. So if u, v, and w are vectors, and we're going to use c as a scalar, the following is going to be true, okay? We can write u dot v will be the same thing as v dot u, okay? It's just like saying a plus b is the same thing as b plus a, or a times b is the same thing as b times a, just like it was back in our early algebra days. What we can say here is that if we go ahead and take two of the same vector and multiply it by itself, or take the dot product by itself, you actually get the magnitude squared. So you end up with the scalar, which is the magnitude is a scalar, squared. You take the 0 vector times any vector, and you, of course, are going to get 0. Your distribution property is very similar to how our distribution property is with anything else. U times the v plus w vector would be the exact same thing as u dot v plus u dot w. And last but not least, if we go ahead and take a look at our property with a scalar, if we have the scalar times one vector, we're going to call that guy u, times, or there's going to be the dot product all right, of v, cu dot product, or cu dot v, we would end up getting the exact same thing as u times the scalar times v instead. So cu dot v is the same thing as u dot cv. Notice the placement could be in either way for that scalar, which ultimately means that you can just go ahead and put the scalar on the outside of the dot product, because you would get the same thing regardless. All right, enough about the properties. Let's take a look at an example first and foremost. So let's go ahead and take a look here at A, and let's find the dot product of the vector 3, 4, and 5, 2. So we're going to go ahead and multiply the x components and add them to the product of the y components. So we have that 3, 4 dot 5, 2 can be written as 3 times 4 plus, 3 times 5 plus 4 times 2. Well, 3 times 5, 4 plus 2, will end up with a value of 23. And that is the real number scalar that we were expecting there. All right, before I continue on, see if you can go ahead and pause the video and do part B on your own. And then we'll continue on. So for part B, 1, negative 2 times negative 4, positive 3 is going to end up producing 1 times negative 4 plus negative 2 times 3. So we get 1 times a negative 4 for a negative 4 minus 6 produces the real number scalar of negative 10. Last but not least, we have it in that linear combination form. So remember, we can always rewrite these linear combinations as 2, negative 1 for 2i minus j. And I could say it's the dot product with 3, negative 5. However you want to visualize it, it all works the same. So finally, 2 times 3 plus negative 1 times negative 5. And we would end up here with a positive 11 for our answer.